Okay, so this is question 2, which is all about our thermal physics unit. A little bit of a mixture of our latent heat capacity and also our ideal gas equation. So the first one was 2 marks. I'm just going to go through. First of all, we were looking at gaseous oxygen, so O2. And we were given the mass of 1 mole, so if I had moles of 1, it was 32 grams. As soon as it's in grams, remember I want to change it into kilograms, so 0.032, or I could say 32 times 10 to the minus 3. The latent heat of vaporization of oxygen they've given me here is 2.1 times 10 to the 5 joules per kilogram. Then it says here, distinguish the internal energy of the oxygen at the boiling point where it's in liquid phase and when it's in gas phase. Remember, internal energy is the sum of potential energy and kinetic energy. Well, it's 2 marks. I might as well just say that in the question. In fact, that was worth 1 mark. So you have to say internal energy is the sum of all the potential energy and the kinetic energy. But you have to say of what? So you have to say of molecules, or you could say particles of atoms. If you just said the sum of potential and kinetic energies and you don't say that, you actually don't get the mark for this. It says that in the mark scheme to only allow 1 mark for the question if they never read molecule, particle, or atom at some point in the question. The kinetic energy of the particles, you could say that here. As long as you've said it somewhere, you're okay. But kinetic energy is the same at the boiling point. They're both at the same temperature, so they have the same kinetic energy. But gases have more potential energy. Remember, in an ideal gas, they can have 0. Okay, and at this point, that's what everything else is wanting to become. So liquids would have a negative potential energy. Okay, solids would be even more negative. They're all trying to become like an ideal gas. That's the potential of what they are. So therefore, they have more potential energy. You should really give the reason as well. So in gases, it's equal to 0. Therefore, there's more internal energy, okay, for the gas. The next one, again, is one of those where they like to trick us with things, with, again, this word rate there. Remember, the IB like doing this. You need to be watching out for it. So as soon as I say the oxygen flow rate of 0.25 moles per second is needed, I've written N over T here. Calculate in kilowatts, so I need to make sure I give my answers in kilowatts, the heating power required. Power is rate of which work is done, so work done over time. The work done here is Q over T, okay, which is ml over T in this case. So we're looking at our latent heat going through. Well, M over T, okay, in this case, I can be looking at the mass of 1 mole of oxygen, but I know I've got 0.25 of them flowing through. So I actually just need to do 0.25 times my 0.032. That also takes into consideration then the mass that is flowing through in that amount of time, because I have 0.25 of my 1 mole coming through every second. Okay, so I can just type that 0.25 multiplied by 0.032 to get that MT in there. Okay, multiplied by my L, which is my latent heat, so just the value that we had from above. Okay, and that gave me 1680 watts. Remember, watt is the unit of power. Again, it needs to give me in kilowatts, so 1.7 kilowatts if I'm giving it to 2 significant figures, which the question was using for all the rest of the parts. Okay, the next one then said, calculate the volume of oxygen produced in 1 second. So in 1 second, remember, we have 0.25 moles passing through it. We have it to expand to a pressure of 0.11 megapascal, so 10 to the 6 is just written underneath, to a temperature of minus 13 degrees Celsius. We need it in Kelvin, which means you get a mark for showing your conversion into Kelvin. So temperature is minus 13 plus 273 to give me 260. I then want to rearrange my ideal gas equation to work out volume. So V is equal to nRT over P. Again, here, my number of moles passing through is 0.25 in 1 second. So I'm not going to be using 1 mole. I'm only having 0.25, so the mole pass through. R, our ideal gas, our ideal gas constant, so 8.31. T is 260. That's really terrible. That should look like it says 260. And our pressure, 0.11 times 10 to the 6. A few little people forgetting about that 10 to the 6 there. So 4.9 times 10 to the 3 meters cubed. So 10 to the minus 3 meters cubed there. It then says the next one, state one assumption that does not apply to oxygen. You can have lots of things there. Ideal gases assume that they are monatomic. Oxygen is not monatomic. Ideal gases assume collisions are elastic. They're not in real life. Ideal gases are point objects. Oxygen is not a point object. There are no intermolecular intermolecular forces. Oxygen does have intermolecular forces. You could have lots of different things that you could put in there. Things like oxygen doesn't liquefy. Also, gases don't liquefy. That's another one for ideal gases. But just one of those assumptions needed to be put in this place.